You have most likely heard the term polyunsaturated fat before. So, unsaturated this is what keeps plant oils fluid at room temperature for the most part. There are exceptions. For example, did you know that in coconuts, that white oily stuff around the edge, the endosperm, that, well, it keeps the embryo alive when it floats for months or years at sea. But the general point is that that fat in the coconut, that is sometimes known as coconut butter or coconut lard or whatever. Why? Because it has a higher saturated fat percentage than lard, as in fat from pigs. That's a lot of saturated fat. But for oils, well, they tend to be, for the most part, polyunsaturated. They tend to have multiple unsaturations. And very importantly, these unsaturations tend to be on the same side, with the main groups on the same side of the relatively rigid double bond. That means that this fat molecule, instead of being a straight chain and falling neatly into line and forming a crystal, like you see in butter or lard, which is mostly saturated fat, this is bent. So it's bent out of shape, and therefore it doesn't fit in nicely. What does that mean? That means it solidifies at much lower temperatures. So, what do we call these? Well, we call these, for the most part, fats that are unsaturated. Okay, basically all of them that are unsaturated are going to be double bonds. So we call these alkenes. Alkynes are what happens when you have a triple bond. Now, we know that a carbon can form 4 bonds. So, we know that normally carbon does this. So we have a bond that goes back, and we have a bond that comes forward. So, these bonds, the angle between any of them is about 104.5 degrees-ish. Somewhere in this realm. What happens when it only forms, well, 3 bonds, say 3 to 3 atoms, or 2 bonds even? Well, this is because of the way the electron orbitals hybridize. And if they don't hybridize as much, what you get instead is going to be carbon, 1 going back, 1 coming forward. So these are all on the same flat surface. This is 120 degrees, and this is 120 degrees. Now the carbon then has this other orbital that basically pokes out both ends. What happens if it has even less hybridization, and so it's just 1 bond over there, 1 bond the other way, and 2 other orbitals that are, 1 comes out of the page and 1 is vertical. This, if there's another carbon here that also has this pattern, these can bond together. That's how a carbon double bond works. Now, if a hydrocarbon has these, well, the definition for unsaturated hydrocarbon is here. So it has carbon and hydrogen. I mean, yeah, okay, hydrocarbon, clearly just carbon and hydrogen. So it has 1 or more double or triple bonds. Now, saturation is an idea that existed long before people actually understood how chemical bonds worked. So before, they used saturation as in, oh, I can't dissolve any more salt. It's full. So unsaturated hydrocarbon essentially means that it's not full of hydrogen. There can be more hydrogen fitted in. Industrially speaking, acetylene and ethylene are 2 commonly used unsaturated hydrocarbons. Ethylene looks like this. H2C double bond CH2. And acetylene is HC, triple bond, CH. So, acetylene, ethylene. Ethylene is technically named ethene. And acetylene is named ethine. The reason why people put up with calling it acetylene is because that name has been used for so long that they are just lazy about actually changing it. And also, if you change the labels on basically most welders' gas tanks, well, that's going to put a lot of them off, which is annoying and not worthwhile. Acetylene with oxygen make for Oxy Acetylene Torches. These are basically fairly standard welding equipment. Ethylene is used to ripen fruit. Ethylene is naturally secreted by plants as a gaseous hormone that prompts fruit to ripen. Fruit nowadays are picked when still green. So, for the most part, if a plant fruit is green, then it's not ripe yet. For the most part. There are some exceptions. Now, alkenes are defined as a hydrocarbon with at least one carbon-carbon double bond. So instead of, say, well, we had ethane to ethene already, so let's use propane to propene. You will notice that I do not quantify that it's one propene. Why? Because there is no other option for propene. Of course, if there were substituents, then I would have to be like, oh, pro 1-ene and say 1-ol. Now, the old method would have been 1 propene, 1-ol. But I suppose this method is better at distinguishing which one is actually 1 and which one is not. Why is it that here I had to write prop 1-ene, 1-ol? Because alcohols actually have a higher priority than alkenes in terms of naming, which means that they would be numbered lower. Although, strangely enough, that's not quite true for alkene versus alkyne. The relationship there is a little bit more complicated. Alright, an alkyne has a triple bond somewhere in it. So, when you draw, say, propene, you draw something like this. But, when you draw propyne, you would draw something like this. Why? Because of the way the orbitals work, while you can draw a double bond in the middle of a standard chain and act like it's all fine, so you don't need to change the angle, for a triple bond, we know that it has to be straight out to either side, for that matter. So, I mean, if we labeled H here on both sides, this would be acetylene or ethine. But if we didn't label them, then this is assumed to be an image of just the carbon skeleton, which means that this is 2-butyne. And this would be 1, 2, 3, 4, 5, 6, 7. So that's a hept, well, 2-ene, or 2-heptene. We note that they typically are not very picky about this, unless there are a bunch of substituents like here. So this is also hept 2-ene, or but 2-ine. Alright, So, aliphatic hydrocarbons have structures that are based on straight or branched chains or rings of carbon. There is nothing special about the way the bonds are hybridized and how the bonds are located. The alternative is called aliphatic versus aromatic. Aromatic hydrocarbons have delocalized bonds, such as benzene, which we'll cover later. But the point is that aliphatic hydrocarbons have bonds that stay where they are and are only between individual particular, well, carbon atoms. So for example, here, these extra electric bonds that are not in the standard hybridized, just these two sharing pattern, those ones stay on these two atoms. Whereas if we had, say, a ring like this, well, this would be this would completely delocalize over the entire ring and it would be benzene. Now, we'll actually talk in detail about that later. Now, alkanes, alkenes, and alkynes are all aliphatic. Technically speaking, you'd think this is an alkene, but no, it's not. These bonds do not actually have double bond characteristics like this lone double bond would. So this is often sometimes drawn as this instead. So with just a circle in the middle to denote how different this is from an actual alkene. Do not be fooled. Now, naming alkenes and alkynes. Well, we still look for the longest chain, but the longest chain must contain as many of the unsaturations as possible. This means that it might not actually be the longest chain. So we're looking for as many of the unsaturated bonds as possible, and it has to be as long as possible given equal numbers of unsaturated bonds on both routes, both options. Now, alkynes actually have priority over alkenes for defining the main chain. What does this mean? This means that if one branch, say this is really, really long, if one branch has a triple bond and the other one has a double bond, well, the triple bond one gets priority. However, we note that when you actually number these things, well, it's a little bit interesting. Oh, yes, we need to mark down enough bonds so that this chain is still counted instead of going this and having this whole thing be a substituent. Why? Because we are supposed to have the longest chain we can have that encompasses as many of the double and triple bonds as possible. So, the bonds are numbered by the carbon where they begin, which means that we would number this 1, would we? Well, no, not exactly. Octatriene would be, let's draw this example. So, octa 246 triene, well, we could draw that in the sense of, 1, 2, 5, well, that's 8. And 2, 4, 6. So 2, 4, 6. And that's it. Now, this we could also write out as CH3, CH double bond, CH, CH double bond, CH, CH double bond, CH, CH3. But that was a little bit long. So, we number these by the carbon where they begin. When we number carbons, well, the total numbers for all the substituents should be as small as possible. But when we're numbering in a symmetric situation, alkenes are numbered lower, which means that in this example here, this end would be number 1 carbon. Not that end. Even though when we name things, well, when we're naming it, we call it an ene. So, of course, there's some number here. And also a number here. And before that, whatever, say hept, something ene, something ein. So the one at the end is the most important group. So for alcohol, it would be ene-O or ein-O. Now, the funny thing is that even though we know that enos can be written as, well, eno, inos, i.e. ein, and then something ols. First of all, usually even enos now are split apart, unless we're talking about ketones versus enos, but that's something else. Way more advanced than we are talking about right now. The thing is, the end group, the end substituent that's named, is the most important substituent. Why does this make sense? Let's think about this for a second. Okay, if this characteristic is the most important thing at defining something, well, people, when they read a word, they have this funny habit of really only paying attention to the first little bit and the last little bit. You can give somebody a document where all the words have mistakes in them. The first letter and the last letter are right, and the total combinations of letters are right, and chances are that person will still be able to use that document just fine. They will still be able to understand it, which is really interesting and probably why they decided to put the most important at the end of the word. And of course, the other important parts are the substituents, which start numbering at the beginning. Although the alphabetical order is a little bit interesting. So, Sis Trans Isomerism. Well, due to the electron dynamics of a double bond, it does not rotate freely. A triple bond doesn't do this either. Think about this for a second. Okay, say we have C and these two bonds over here. I'm not bothering to indicate the orientation. This is what you do for go back, and this is what you do for come forward out of the page. This is supposed to be filled in. Now, if you have an electron orbital that looks like this, and it's hybridizing, well, not hybridizing per se, but bonding with another electron orbital here, then these essentially pool together more or less. So, if these are pooled together, do you think that these carbons can rotate freely as if it was just this one bond between them? I mean, clearly not. If you try to pull these out of alignment, it will cost a lot of energy. Which is why alkenes are considered to not undergo cis trans isomerism readily. That means they don't switch between the two forms readily. That means the two forms are both important and, well, both affect the reactivity and other characteristics of the particle, of the molecule. So, you have probably heard of trans fats at some point or another. Trans fats act like saturated fats, but worse, according to certain sources. Now, saturated fats, they line up neatly in long, straight rows. But these things still wiggle about. They wiggle and flail around. So, a saturated fat may well curve itself into a structure that looks like this. And not be in a nice straight line. A trans fat, on the other hand, well, if you have this, that bond is basically locked in place. which means that it can't wiggle about, it solidifies even more readily, and in general is even less healthy for you than a typical saturated fat. Of course, too much fat of any type is not good because it contains more energy than sugar of the same mass and volume. Hence why plants rely on oils and fats to move. Why do animals use fats instead of glycogen or starch like plants do? Plants use starch, animals use glycogen, which is a little bit more efficient in terms of just storing sugar away ready for use. But for long-term energy storage, animals use fats because they move. Plants use fats when they have to move, when space and weight are issues, such as seeds. And even clones. For example, the dandelion seeds you see, those are not seeds, they're clones, as discussed in science class. Stereoisomers have the same chemical formula and structural backbone, but the different arrangement of atoms in space are what makes them, well, different. So, if we know that a double bond is locked in place, then we know that this is going to be a different particle, different molecule than this. What does this tell us? Well, this here we call a trans isomer because they're on different sides. A cis isomer is if they're on the same side. Now, groups of interest, that basically means the highest priority group. How do we determine priority? Okay, so we look at, okay, these are hydrogens and these are CH3, CH3, and hydrogen. So, we know that C is a bigger number, atomic number, than hydrogen. What does this say? We prioritize the higher atomic number when we talk about stereochemistry. And we order the groups by atomic number of the first atoms if needed. If the first atom is the same, then we go to the atoms it is bonded with. Whichever one ends up having the longer chain, if they're all carbon and hydrogen, or alternatively, whichever one branches out first, wins. So,